is I just posted a whole bunch of stuff. So, and I'll pass back the exam 3 here in just a second. But let's talk through the materials that you have accessible to you. So, just like with the other exams, you have a post-exam 3 grade. So, I believe if you click within the modules, this is week 14, I think, you can click the post-exam 3 grade and it'll tell you your score for that assignment. Okay, so let's just pick, let's pick a 0.81. I don't know, just pick a number. Okay, so that's going to translate to a B. I believe Canvas will tell you both the decimal value and the letter. Okay, the next kind of sequence of things, we've got 4 pieces. Okay, the first one is your average final prediction. So this post-exam 3 grade now takes into consideration a lot of material. You now have all of the smart work that you've done so far. You have most of the paper homework. It didn't include paper homework 7 because I did the calculations before that was input. It's got the play posits and it's got the exam. So really the only thing mostly left is the final exam, which makes up a big chunk of points. So the post-exam 3 grade, if you maintain your current effort with everything, that's roughly what you should be expecting. Okay? There can be some changes within that, but that's largely what that means. So if you've been doing all this smart work and getting perfect scores, you need to continue doing that, and that's what that post-exam 3 grade would be. If you're getting 90% on those, then that's what you need to continue doing to get that. Okay. The post-exam 3 grade also assumes that you score your average of your semester exams on the final. Okay, which can be a big assumption. Sometimes it is, sometimes it's not. The ACS, there's a wide variation in kind of outputs, and I think some of that might actually be due to all this information that you get at the end. Okay, so the average final prediction is now out of 70 because the ACS has 70 questions, and it'll be a number. Okay, again, I'm going to take a swing at it and say that your number for that was 38. So what that says is that you are expected to get 38 questions out of 70 right. If you do that, that post-exam 3 grade is your letter grade. Okay? That's what all that assumes. After that, you may be looking at that B and being like, I don't want a B, I want an A. Okay? So you want to advance a letter grade. That's what that next category is. So in that next category, again, still out of 70, because the exam is 70 questions, you're going to potentially see a new number. Okay? In this case, you want to go up a letter grade, so it's going to be more than 38. Okay? And we'll walk through a couple different examples, which mathematically won't make sense, but that's kind of irrelevant. Let's say it says 50. Okay, so to advance a letter grade, you need to get 50 on the final, 50 questions right on the final. Okay, if you get that 50, I guarantee that you will advance a letter grade. Okay, that does assume, again, that you maintain your current performance on everything else. Okay, but if you do all that, that's an advanced letter grade. Okay. For the record, this is now kind of a more important number. So if we now look at what you need to get on the final, if you want to advance to an A, it's not a 70 question exam. It's a 50 question exam. Okay? The trick is that those 50 questions are scattered amongst 70. So there's 20 distracting questions. You need to find your 50. So this is a different strategy when we look at the final than it is to the semester exams. Because at this point, you have a target that you need to hit. So a lot of people will go through and say, well, I only get a minute and a half per question. That's true for a 70 question exam. It's not a 70 question exam. It's a 50 question exam. So that means you have more than a minute and a half per question. Okay? But that means you also have to be very smart about what you're selecting and not looking at or wasting time on questions that you don't know. Okay? Which will happen. There's going to be questions you don't know. So you need to guess on those and move on as quickly as possible so that you're not wasting time. Kind of makes sense? So that's our first kind of baseline interpretation. The next level, kind of deeper interpretation, is we can now compare that advanced score back to the average score. Based off of your current exam average, you're expected to get 38 questions. To advance, you need 50. That's a 12 question difference. Yes. Okay. Is that something you can do? Yeah, I absolutely 100% think that that is in the realm of possibility for everybody. Okay? Does that mean you have to work harder? Yes. Without a doubt, you need a significant change in your performance to jump up that many questions. Okay? So if you're looking at that and you're saying, I want that A, that's your target. You need to change how you've been working the entire semester to make sure and increase to make sure that you can get those extra 12 questions right over your expected average. Does that make sense? Okay. That's a relatively big jump. So maybe somebody looks at that and says, that's not worth it. I'm not going to deal with that. We'll look at the next interpretation for the next thing in a second. If you saw a 40, right, that's only a 2 question difference. To me, that means you should work harder. That's a very subtle change in your overall performance. You're looking at almost just raw guessability difference between what you're expected to get and what you need to get an A. I think you should invest even more time than you've been investing to try and hit that A. That's 50 score. I would leave that up to you. That's going to come down to what you're doing in your other classes. So this is trying to provide a little bit of guidance to give you an idea of what you need to do, and then you can decide based off of your schedule and your personal life whether that's a reasonable target or not. Does that make sense? Last thing I'll drop in here, because sometimes it happens, you see nothing for the advanced final. Okay? What that means is there is no score based off of your current grades that would allow you to advance a letter grade. Okay? So it could mean that you have an A. Okay? You can't advance if you have an A. It could also mean that maybe your B is so low that even if you get a perfect score, it's not going to advance you. Generally speaking, that's not the case. The reason your final doesn't advance you is not because of the final performance, but because of your smart work, your paper homework, and your play posits. That there's weaknesses or deficiencies within either one of those 3 that is now sandbagging your ability for the final to actually make you jump a letter grade. Okay? There's very few students in that category, but there are a couple that are leaving 5 to 10% of their grade on the table. Just saying they don't want it, effectively. Okay? It is those people that are going to have a hard time with this advance on the final category. Okay? And it's a much harder calculation because now you don't have a raw number to look at. Okay? Because you have to change multiple variables. Kind of make sense? Next thing, so say it was a 50, let's be dramatic. Let's call it a 60. 22 question jump is possible, but that's a lot of effort. You've got a personal life going on, lots of things happening. You've got other classes. It's not worth your effort to try and make the A. Fine. Okay. Now your focus is going to shift because you don't care about making the A. What you care about is not losing the B. Okay? That's that last category, the maintain. So if you want to maintain a B, how low can you go? So the advance was going higher. Okay. Now it's how low can I score? Okay. So generally speaking, I get a bit itchy drawing numbers that are real low. Like in some cases, I've seen numbers drop as low as 10 questions, right? Okay. Out of 70. That bothers me because what that means for that individual student is how much effort do they have to put in? Absolutely none. Which means what happens to the exam average at the end? It goes through the floor because someone played the system correctly, which is fine, I get it. they played the system correctly, but now they make the end result output look like shit. Okay, so I try to avoid numbers that are that low. Okay, I honestly don't remember where I sat this time. Okay, but 20-ish, I think, is as low as I would actually mark. So you could potentially score even lower and still maintain your grade. And you're now in an area where I just don't want to tell you that you could score lower because I don't want you to score lower. Does that kind of make sense? Okay. And we'll talk a little bit more about that too. So if we said it came back at a 20, you're expected to get 38 questions. To maintain, you only need 20. Okay. I would argue, yeah, you don't have to do much work. Just kind of float through the rest of the semester. You could probably ignore this entire last unit, okay, and just focus on the past stuff and you'd be fine. Okay. 20 questions should be a decent target to hit, a relatively easy target. Okay. The hard part with 20 questions is that there's 50 distracting questions that are going to break your brain. So you have to be very careful to pick the 20 questions that are absolutely critical to what you want so that you can maintain, and then you can go through and guess for everything else. Kind of make sense? Okay. So that would be an optimal scenario if you just wanted to maintain a B. Okay. Again, the numbers change for every individual student. So let's say it came back and hit you at a 37. What does that mean? Yeah. If you want to maintain that B, this is a significant amount of effort. Okay? You have to ensure that you don't falter at all with your exam average. You have to effectively hit that 38 number. Okay? So that's not taking it easy. That's maintaining your current effort as best as possible and arguably probably working a little bit harder so that you get a little bit of a buffer. Does that make sense? Okay. If you hit that 37 though, that's a guaranteed B. That's what these numbers mean. Okay. So if you hit that magic number, that's done, you're fine. I will double back through and check and make sure you still completed the smart work for this last unit, you still did the play posits, and you still did the paper homework. But as long as you've done those to your average, the final output's what it is. Make sense? Okay. The last thing that I'll mention is that these are current estimates based off the final. I'm guessing at the future. The future may change things around and make it more, maybe performance is lower, okay? If performance is lower, I might drop those numbers even lower, okay? But now what you're relying on is an end of the semester curve beyond what I'm already predicting, because this does factor in a curve for the class, okay? That's a risky case to be. Okay? If you've ever heard sports don't let the referees make the decisions or allow you to win or lose a game, okay? Don't put it in the random point falling at the end for you to get the grade that you want, earn the grade that you want outright. Don't let it come down to random will at the end. Kind of makes sense? Almost invariably, someone will ask, well, how's the extra credit factor in? The extra credit does not factor in, period. It doesn't. I assign the grades. Once the grades are assigned, now I look at extra credit. Okay? And if you're in that borderline category, yeah, I'll look at the extra credit to see if it bumps you up. If it does, you advance. Okay? But grades get assigned before I look at extra credit because we have a curve. If I look at extra credit before grades are assigned, it's not extra credit. Okay, so it is strictly done as an extra credit system. I want to make sure that that doesn't taint the overall grades. Okay, as a rule of thumb, it's about 10% of the class that ever sits in that borderline case that could benefit from the extra credit. Okay, with only 8 students in the class, that's like one person is going to need the extra credit to change their grade. Okay? Arguably, the extra credit is improving your grade already. Okay? But one person will need the extra credit. Make sense? Questions about that data? No problem sitting down with anybody if you want to go through the data individually. That's something that should be semi-private. We can probably pull that off in office hours. Even then, we might go out onto the balcony where there's less people and talk through grades there, so that nobody else has information about it. Okay. To that same point, you shouldn't be sharing your numbers. Those numbers have grade information in them. Ignore them. Don't share them with other people, and you shouldn't ask other people either. Okay. Grades are yours personally. You should not be expected to, nor should you be asked to share your personal grades. Make sense? Okay. If there aren't questions about that, I'll go ahead and pass back the exam. So, if we're going to look at smart work, officially they didn't ask the proper question, right? But yes, they are saying to draw resonance. Along those lines, did they provide structures in all those boxes?
Yeah, this is blank place. It's the same one, but without the pylons. So it's the same from the first box, but just without the pylons. So it's like blank in the middle.
Okay, I think so. They provide you a skeleton-ish structure. Okay, I get it. So then, within that context, really, what we should be doing is just starting with the first structure. Okay, and if they don't really provide any more context, how would we know we should be drawing resonance structures? Those arrows mean resonance, which means everything we should be doing should be resonance. Okay, what does resonance mean?
Moving electrons.
Any electron? Okay, moving electrons. And the electrons that we're allowed to move pi electrons. Is that it? And lone pairs. Those are the only electrons we're allowed to move when dealing with resonance. We cannot move sigma bonds. Sigma bonds are locked into the structure. The only way we break or move a sigma bond is by running a chemical reaction. Chemical reactions are not resonance. Why all that emphasis? What's this very first arrow show? Sigma bond moving. Right out of the gate, that's a problem. Okay. So that structure is bad. So we've got it mostly redrawn down below. Okay. If that's what they gave us initially, okay, and I'm making an assumption there, I honestly don't know if that's what they gave us. Okay, we should ensure that what we're looking at is a proper structure. Is what we're looking at a proper structure? What's wrong with it? That particular carbon with the green dot is missing its octet. So either there's another hydrogen there, which would be really suspicious considering they showed all the other hydrogens, or we're missing a charge. Okay? The question could then become, well, what charge are we missing? Okay, this is where I would scroll back up to the top and it says the uranium ion. And if I don't know what the uranium ion is, that's okay. What should I do? I should look it up. And when I look up the uranium ion is a cation. It is a positively charged structure, which means that carbon should be positively charged. Okay? So if they did not give me that positive charge, I need to make sure that positive charge is drawn in there. Okay? Now I want to do resonance. To do resonance, I can move electrons, either pi electrons or lone pairs. Does this structure have both of those? we should work on some review here. Because in that scenario, that was, does this structure have pi bonds and lone pairs was the question. Yes, absolutely, that was a 2-second question, or a 2-second answer. We should be able to look at that, see that we have double bonds, and we have lone pairs in the chlorine. Okay, so absolutely we have both of those. So now the question becomes, what should we move? Okay, why do we want to move the pi bonds? Okay, they're the only ones we can move. You mean you can't move the lone pair? Why not? Sorry, that was a little weird.
Not where we're focusing on?
Okay, I can accept that. If we look at our primary issue within this structure, the primary issue is the carbocation, not positive carbon. Right? And if we look to where the lone pair is located up on that chlorine, it's further away than the pi bond. So it makes more sense to look at the pi bond than it does the lone pair, because the pi bond's more directly conjugated with it and can make up that system. Which brings in the question of conjugated, so now I'll let you jump in.
I was going to say that if you move the chlorine's low pairs, you exceed octet on that carbon.
If you move the electrons from the chlorine down, we would exceed the octet on that carbon. Call it our purple carbon. Chlorine would have a charge, okay? But when we're dealing with resonance, charges are going to appear and disappear kind of at will as we move things around. So it's not necessarily bad to do that. Okay? It can be a little bit weird and goofy, yes, but in this particular chapter, there is reference to actually making the double bond between the halogen and your carbons. Yeah. Okay? So, but the bigger issue is that purple carbon would exceed its octet, which in and of itself isn't necessarily a bad thing, because typically when we do resonance, we exceed octets. So that just means we have to move more electrons. But the electrons, the only electrons we're allowed to move are pi bonds or lone pairs. And if we look at that purple carbon, there's no pi bonds to move except the one we just made with the chlorine, which means I would add another arrow to show the electrons go back. The resulting structure would be identical to where we started. No resonance. Okay? Another cheat that we could go through and do with enough practice is that we might notice that purple carbon is sp3 hybridized. It's a tetrahedral carbon, and as an sp3 carbon, it can't pass electrons through it. The only electrons that can pass electrons through them would be sp2 and sp. Why? Do better, but that's an awesome answer. They have an orbital, yes. What orbital do they have? They have a p orbital. It's not necessarily empty, right? Because if it's a double bond, it's not empty. It has electrons in it, okay? But they have p orbitals. Those p orbitals are what's allowing resonance, okay? Which is why, what electrons can we move? Pi bonds, because pi bonds are made up of p orbitals, and lone pairs come in this weird gray area. Okay, lone pairs, you might be like, well, aren't those sp3 hybridized? Yes, but if we tweak the angle of the structure just a little bit, we can cause that hybrid lone pair to rotate up into what is effectively a p orbital, allowing for resonance. Okay, so it's looking at subtle tweaks to the molecule, causing an increase in conjugation, and that conjugation is a stabilizing feature. Okay? So enough review, we can double back and say, okay, we want to move the pi bond. Where do you want to move the pi bond? Okay, we can move it up. We'll go bond to bond. Okay, say that again. I could also move the other one. Okay, which isn't necessarily wrong, but you're in a scenario where you have to draw multiple resonance structures, right? So what you're trying to effectively do is draw all resonance structures. If you start doing multiple arrows when you don't have to do multiple arrows, you could be skipping over valid resonance structures and may miss those intermediate ones. Okay? So it's not that it's wrong, but in this particular scenario, we probably don't want to do that, and we want to focus instead on just doing the simplest action possible. After we've done that arrow pushing, we could go through and note that nothing else changes. I'm not drawing the lone pairs on that chlorine again. Fine. Okay. That double bond didn't move, so I don't care about it. The other double bond did move to that spot. Okay. Is my structure now good? What's wrong with it? That bottom carbon must also be positive. Okay, now what can I do? Now I can go through and move the other pi bond. The pi bond on the right didn't change, so we'll revert that back to red. Oops. Do we have our final answer? We're still missing that charge. Drop on that positive charge. What we've now shown is what's known as our sigma intermediates for a particular reaction. We don't know where this reaction necessarily came from, but with enough background knowledge of looking at all the reagents behind it, okay, what happened is we started with benzene and we reacted it with chlorine, probably in the presence of a Lewis acid catalyst. Okay, and this was on the way to doing the formal substitution back to our final product. So really what this question is asking is, do you recognize how to do resonance? That's it. When did we learn about resonance? Unit 1 of semester 1. When did we use resonance? Every unit thereafter. Okay? So we should be awesome experts at resonance, and when you see a question on the final, you should be like, oh, this is resonance, this is easy. I know this. Okay? Because you're following the exact same patterns that we've been using constantly throughout the semester. Make sense? Okay. What next? Just because I'm a smartass doesn't mean you can be one. What did we do? What did we do to try and solve that up on the boards?
I identified charges.
We didn't identify charges first.
Reactive site.
Okay, we could kind of push to reactive sites, but I would argue we didn't even do that. We identified the new bond. Okay? To identify that new bond, what did you do? We looked back at our starting material and we tried to find the most common pattern. So theoretically, you went through and saw that you had this and you had this. Okay? The aluminum trichloride didn't show up anywhere in our answer, okay? Which means it didn't contribute to the final structure, but then that meant that whatever was missing had to show up in that box. So we could go through and show that structure. Okay? We then have to decide our charges. Okay? How do we want to do that? Okay? Or radicals. Okay? Radicals is kind of, to me, I would argue you should just ignore radicals. If you think there's a radical system involved, guess and move on. Okay? They just don't make up a significant portion of the chemistry within the class. It's not worth the effort to really deal with. That said, they are very powerful. They will show up. Meh. Okay? So we then went through and said, well, what if it was positive and negative? Okay? In those scenarios. Well, did we like that? Did that make sense? That didn't make sense because that put a negative charge on a tertiary carbon. That's less stable. We could still do things like that, but that doesn't make as much sense. We could then also go through and look at the positive. Well, the positive on a benzene ring, that's not particularly likely. Okay? Add the fact the benzene ring was not directly altered from our starting material. Right? So that carbon didn't start positive. Somehow during the reaction it would have to become positive. That seems a bit sketchy. So what if we flipped the script on that? And we said the carbon started negative. That was a dumb statement to make because they're both carbons. Okay, our blue one was negative and our red one was positive. Well, does the red one make sense to be positive? Well, that's a tertiary carbon. That could make sense to be positive. Does the blue one make sense to be negative? Well, what's reactive in a benzene structure? The pi bonds. And what are pi bonds? Source of electrons. That's effectively a negative. There we go. Both of those pieces would suggest that this was the best system that we have to go through and assemble. We then have to decide how we get that positive into that particular carbon. How do we decide that it should be a chlorine? What did you look for to see that it needed to be a chlorine? Say again? That's where we shifted back to the catalyst and said, what does the catalyst go through and do? Okay. Admittedly, we just thought through it all, but Irvin did a really good job later drawing it on and showing how the Lewis acid catalyst would react. It's got an empty p orbital because it's sp2 hybridized. Those electrons from our chlorine can dump in there, which helps to polarize it, which allows for the nucleophilic attack into that position, thereby forming our rhenium cations, which I think we recorded just a little bit ago, right, that can then break down and ultimately get to our final product. Cool? Okay, so we're going to backtrack a little bit, try something a little more exciting, a little more fun. We know that carbon needed to be positive, right? And we said it because we saw aluminum trichloride. Now there's no aluminum trichloride. This also adds an extra whole layer wrinkle beyond it that I didn't want to do, but how do you get that carbon to be positive if what you're adding is H+? What would H+ need to react with? A negative. But our purple structure is positive. So what else would need to be in our purple structure? Did you intentionally do that? Where do you want to put the OH? The carbon I'm pointing at? You're such a jerk. Talk through your chemistry. Confidence, you got this. What would the acid react with? What on the lone pair electrons. And if we converted one of those lone pair electrons into a bond with a hydrogen, what would happen to the oxygen? What? Not quite yet. It would be positively charged. Oxygen doesn't want to be positive charged, so what can it do? It can leave. In the process of it leaving, what does it produce? There's your positive charge. So there are multiple answers that we could put into what that starting material was, but it's all heavily dependent on what's the catalyst. And you say you already did this one, and that's why you got a variation on it?
Yeah, because there's 3 different parts, and I think it had H2SO4
Oh, son of a
and
bitch.
H2O3. I think. Thought it was another question.
Okay, it's very possible. It does say part 1, so you could very easily be right.
Yeah, part 3 is in here.
Okay, how else could we have done it? What does that H2SO4 need to react with? Okay, and since you've already said you've done it, you can't answer anymore.
Should it be nitrogen? Is that non-service?
Except that nitrogen's not great for leaving groupability. So what you're trying to do is follow that exact same vein of the oxygen all the way through. There's another option. What does the H plus need to react with? What did it react with on the oxygen? Lone pairs. What are lone pairs? Electrons. What if I put lone pairs on that carbon? What would happen to that carbon if it had a lone pair? Slow just a little bit down. You're both saying the same thing, which is lovely, but I want the previous information that allows you to say that first. If I put a lone pair on that carbon, what do I need to change about this structure? What was that, Abby?
Charge.
What charge?
Carbon.
Yeah. Yeah.
Could be negative.
Yeah, it would be negatively charged. And if we had a negative charge next to a positive, that would be a good reason to do some resonance to try and cancel that charge out. And if we did that resonance, what would we end up forming? A pi bond. That pi bond would now act as a base, do an electrophile addition with the H+, lose the pi bond, form a carbocation. The carbocation can now react with the aromatic ring. So we're looking at subtle ways to change the information to allow us to navigate it. Kind of makes sense? And because it's a three-part question, I believe we just accidentally walked through, because that was not in my intent, we just accidentally walked through all three parts. Right? Though I do want to point out a potential complication that I don't think they point out in this particular question. In two of those, the last two we talked about, with both the pi bond and with the OH, what was the clutch thing we ended up forming that allowed it to react with the aromatic ring? Okay, in the last two reagent systems, we had an alkene and we had an alcohol that reacted with the acid. Both of those formed a clutch or important intermediate that could then react with the aromatic ring. What was that intermediate? The carbocation. Fantastic. Why are carbocations potentially problematic? There it is. As soon as we form that carbocation, particularly next to that 5-membered ring, I would actually bet we're not going to get the product shown if we form a legit carbocation. Because more than likely what I think is going to happen is you would get the rearrangement up to a 6-membered ring. Then you would run the EAS reaction. Okay? At very least, it would be a complication of this that would then reduce the overall yield. Okay? So we do have to be aware of that if we're forming carbocations in any of our EAS reactions, rearrangements are a distinct possibility and an added complication behind the potential outputs behind these. Kind of make sense? Okay. That, I'm going to delete all that work. Maybe. Thought I was going to delete it all. Let's try again. There it goes. So they did aluminum trichloride, phosphoric acid, and sulfuric acid. The difference between the phosphoric acid and the sulfuric acid is the sulfuric acid is the stronger acid. I would bet the sulfuric acid wants the alkene. Because remember, alkenes are not particularly active. Josie's shaking her head yes, which I guess means that's how it panned out. Yeah. Phosphoric acid being a weaker acid could be used to react with the alcohol because the alcohol is more basic than an alkene. If we think back to our electrophile additions, both at the beginning of this unit or this semester and at the end of first semester, our alkenes are very unreactive. You have to force them to react by reacting them with strong acids. How do I know phosphoric acid is not a strong acid? It's an unpleasant answer.
Memorize.
Yeah. Back in Gen Chem, when I taught Gen Chem, I told students that they needed to memorize the common 7 strong acids so that you could answer questions within Gen Chem, particularly 152 is where that shows up. Okay? It shows up again in organic chemistry because it allows us to interpret the different reactivities behind those. Okay? Sulfuric acid is one of the strong acids. Phosphoric acid, while a stronger acid, is not a strong acid. Its pKa is in the 2 to 3 range, I think, for that first hydrogen, whereas sulfuric acid is, I think, -7. Okay, so significantly stronger of an acid. So having some of that information from Gen Chem can help us in these later kind of questions. I don't think you would get nuances like that on the ACS for the final. Okay, but smart work. It makes sense. It makes sense to kind of push you on that. Okay? Those 3 parts, so we're done? Yeah. Sorry. For the sake of the recording, very similar to the questions we just walked through. How should we start trying to solve this question? Not necessarily bad, so look for the chemistry. So where are you telling me?
Like where the new bond forms.
Okay, so slightly different phrasing, I would argue, is what we want to do is identify the new bond. So we've got a new bond moving through there. Okay, so that new bond is going to split. Okay, again, how does it split? Positive, negative, or are we splitting into radicals? If we make, again, the blanket statement, it's not radicals, let's look at charges. Okay, so we could be negative, positive, or we could be positive, negative. Which one makes sense? Red or blue? Why blue?
Carbon on the carbonyls be positive because of oxygen.
Okay. So we could just look at our final product. We've got kind of a resonance effect that's going to suggest that that carbon should be positive and that carbon should be negative. Okay. I would argue it's not an argument, it's just another place to look. We could go back to the starting material and recognize that that starting material is already there. And if we look at the reactivity of that starting material, that carbon is absolutely going to be positive. Now I scribbled out the chlorine. Okay? Which means our answer choice, whatever this is reacting with, needs to have a negative carbon. So I go through my answer choices, and do I have negative carbons in all of them? No, I don't. Okay? So a really good opportunity here would be to
Not the one you know is wrong.
cross out the one that we know is wrong. So in this particular case, this person's work is good. They've crossed that out. To me, I would get more aggressive. Okay? And I would potentially push it even further. Oh, it looks like they already did that and crossed out A. Because I know 3 can't be an answer. Okay? I am now saddled, unfortunately, with the nasty problem of all the other possible options with the remaining 2 answer choices. Okay, 1, 2, and 3. If we go through and look, they both have the right number of carbons. So how do we piece it out? What's that? I would kind of agree with you there. What are you memorizing?
That strong lithium carbonyl thing would react twice in form.
Okay. If we look at that ionic bond is as extreme as we can get. We're looking at lithium at the extreme left-hand side of the periodic table. We're looking at the lowest possible electronegativity we can get. Carbon being where it is, okay, doesn't really change, but we're looking at an extreme difference, which means that is a wicked strong negative. And if it's a wicked strong negative, what is it going to do when it sees the positive of our ketone product? It's going to react. Okay? Which theoretically we could have remembered from Unit 2 when we studied how the negative lithium attacks aldehydes and ketones. Okay? So we have some of that background knowledge. That doesn't mean it's stuck. That's fine. Okay? But that's one of the reasons why we try and push to that content. The next part, okay? So you've memorized that that is just wicked and is going to react twice. And when it's going to react twice, it is therefore not the answer, right? So it can't be 2, can't be D, which means you're saying C, just 1. Okay? So cool, that's fine. How else could you have done it? Still memorization.
You just memorize the Gilman reagent.
With that copper, we're looking at a Gilman reagent. The Gilman reagent was a weaker nucleophile. Again, back to Unit 2, the Gilman reagent did not react with aldehydes and ketones. It only reacted with the alpha-beta unsaturated ones. It's reacting with the alkenes. Okay? Which means if it doesn't react with the ketone, 2's out, 2's out, which leaves us again with just C. And it's just going to react once with the acyl chloride. Okay? All of that is trying to fall back on old content. Do we have the option to be able to fall back on new content? Yeah. If we look at the spider diagrams for our acyl chlorides within Unit 3, it does show the Gilman, and it shows it forming only the ketone. So you could be going back to the new content to reference that. Okay? It's a lot of reactions. There's going to be holes. Don't stress about it, but try and figure out how you can plug those holes. Make sense? Careful there. Questions about that one? You good?
Yeah.
Okay. It was your question, right?
Yeah.
Yeah, I was just checking. Solve.
Oh.
It's
L, Y, S, I.
Okay, there we go. It's just one of them fancy O's. Oh, wait. Fancy O. Okay, so what I would try and push you to do is to look at kind of the language behind what's going on in this. Solve is what? Solvent. Now the harder one, lysis. So hydrolysis is the same thing, except the solvent in hydrolysis is water.
So reaction salt is the.
So it is a reacting with the solvent. Typically what it's meaning is cutting. Okay. Which, for those people that move into biochem, you'll find this showing up in a lot of the biochem enzyme names. They'll reference different names based off of what the enzyme does. So if you have some Greek, Latin, root language, that might be able to help you process some of what the enzyme is doing. I will comment that's a little bit tricky because the name is dictated based off of how it was discovered. Enzymes have the ability to go both directions. And generally speaking, sometimes it's easier to discover the enzyme by going backwards than by going forwards. So you can get enzymes called synthases. Well, what is synthase going to do? What does synth sound like? Yeah, synthesis. I'm putting things together. So you'll get a synthase that when it's actually doing its biochemical function, it's breaking things apart because of the order and how it was discovered. So be aware of that. So when we're talking about solvolysis, it's really just solvent cutting. I believe that question is in here because that came up a long time ago with, I think actually just a practice ACS exam. They used solvolysis and people were like, I don't know what that means. Yeah. Yeah. And if you don't know, you don't know. That's fine. Let me flip to 28 real quickly to see if I can get some secondary content on that. Sorry for the paper rustling over the microphone. Yeah, I would argue that's kind of my fault because what I should have done for that particular question, because it just says which of the following compounds would undergo solvolysis at the highest rate, okay? When I'm trying to introduce a new word like that, I almost always try to also include reacting with water. Okay, so that you could try and, if you didn't know the word, the chemistry was written out in a way that you could come up with that system. So yeah, what that question is talking about is how do you cleave the acid bond?
Wondering which one is it.
Oh, so yeah, if you're looking at solvolysis, the highest rate needs to mean it's going to react the fastest. If it's going to react fast, it's got the highest energy to start. So really it's just, where are you on the ladder? Are you at the top of the ladder? That's going to jump real fast. Are you at the bottom of the ladder? That's going to be a slow reaction because there's no energy differential. So in that particular case, it's C, which gets a bit tricky because that's an anhydride, but it's hidden within that double ring system. And I apologize, I didn't put that in the video, but you could hear the language. Are we ready to look at question 3? Dun, dun, dun. Yeah, okay. Okay. Because you don't have an attempt on this, do you?
No.
Dang. What does that mean? Yeah, to the boards. So yeah, this one is mostly just a memorization and a little bit of review. The sodium borohydride isn't a choice question. The reason this question is here is for that tin HCl. Okay, because that tin HCl does some useful chemistry with the nitro. It does that as a full reduction to the amine. And that's an important chemistry to know because you will see that reduction. The sodium borohydride is review chemistry, and really that's there as an acknowledgement that it can't reduce the nitro. But it should reduce the carbonyl based off of the standard chemistry out of Unit 2. And for the sake of the recording, I'm not going to tell you that answer. You just got to look it up. Or you remember it. Sorry. With that, I think we're done.